acceleration due to a force F when applied on a particle mass M. Now, this thing here is the inertial mass. It's the amount of resistance when you push on something, you exert a force on something. It'll accelerate. The resistance to that is the amount that diminishes. The amount of acceleration that will result from the force F is diminished by the amount of resistance. Clearly, the larger the force, the more the acceleration. The larger the inertial mass, the smaller the acceleration. So this is inertial mass. Right? You have a law K Q over R squared in electromagnetic, right? Electrostatics. The Q has nothing to do with the mass. It's a totally different thing. They have two charges. They attract each other or repel each other. That has nothing to do with how much resistance to motion there is. Now, Newton's law of gravitation is you have some kind of constant. The force between two masses, mass big M and mass small m, separated by a distance r squared. The larger the masses, the more the force, the more the distance between them, the less the force. And that's some kind of constant. But this is a different mass than this. This is the gravitational mass. The attraction of two particles to each other has nothing to do with the amount of resistance to motion. This is basically a gravitational charge. It's a Q for gravitational force. It's a different quantity. It's the amount of whatever gravitational charge that they have. And they're attracted to each other by this gravitational charge according to this equation, which again is very beautiful and as simple as possible. The stunning and totally unexpected thing was that it turns out that these two masses are the same. In other words, the property of mass that it has, that it resists your motion, your attempts to move it, to accelerate it, turns out to be exactly the same as the property of mass which causes two masses to attract each other. There should be no relationship between those two things. This is basically a gravitational charge. It's a Q for gravitational force. But it turns out that they're the same. How do we know that they're the same? Because if you drop two things, they have the same acceleration. In other words, if you put this force in here, instead of this F, if you put this in here, what will happen to the M's? You'll have the acceleration due to gravity will be this M G over R squared divided by mass inertial. Now you can't cancel anything out because this inertial mass is gravitational mass. It turns out though that this amount is equal to Gm over R squared, which means that these two did cancel out. That's the only way. These things are independent of the particle. This is the mass, let's say, of the Earth, and this is the center of the Earth, G. The mass of the particle itself doesn't come into the equation, which means it predicts that if you drop two particles of different masses, they will follow the same acceleration. That could only be if this mass and this mass cancel out, which could only be if the inertial mass is exactly equal to gravitational mass. And this is like an extremely, extremely strange thing. And we'll see later how it leads to general